All right, IBAASL2. Today we're doing more antiderivatives, more integrals, but we're going to get into some slightly more complicated ones and finding some C values and learning a process called U-Substitution. So before we get to U-Substitution, I want to talk about some examples where you actually find a specific C value, because up until now we've just been leaving that C on the end, letting it hang out. But today, or with certain problems, you can actually find the C value. So here they have given us a derivative of a function, and they gave us some information about the original function, that if you put in a 1/2, you get out a 4. So we're going to find the entire original function. First step is we are going to integrate 2x minus 3 cubed dx. To do this, well, first of all, it's a composite function. It's like a chain rule happened, because there's an inside function. This inside function is 2x minus 3. But when you take the derivative of the inside, you should have gotten a 2 out of that. So what we're going to do is balance things by putting a 1/2 on the outside. It's kind of like, one way to think of it is that you're actually putting a 2 in there. So you're like putting a 1/2 on the outside and then putting a 2x minus 3 cubed dx, because then this 2 and this 1/2 just cancel each other out and give you 1, and you get the original function. So you're not really changing it. Okay, so now let's actually run the integral. That's not the right tool. So this would be 1/2 times 1 over 3 plus 1, 2x minus 3 to the power of 3 plus 1. So that's the reverse power rule. And then all of this would get a plus c on the end. Now, when you clean up these fractions here, you get 1/2 times 1/4, which is 1/8. So that means the original function is 1/8 2x minus 3 to the power of 4 plus c. Now that is the original function, but this c is just hanging out, and we can actually solve for that c using this information right here, that if you put in a 1/2, you get out a 4 in the original function. So I'll replace the f of x with 4. I replace the x with 1/2. And let's solve for c. So 2 times 1/2 is 1 minus 3 is -2. So this is 4 is equal to 1/8 -2 to the 4th power. 2 to the 4th is 64, is that right? Just checking. No, 16. I'm thinking 2 to the 6, my bad. So then 16 times 8 is a 2, so we get 4 is equal to 2 plus c, so 2 is equal to c. Beautiful. So the original function is 1 over 8, 2x minus 3 to the power of 4 plus 2. Next up, g of x, that original function, goes through this point. Are you guys seeing a theme here? That it's like they give you a point on the original function. That means that you can solve for your c value. The derivative of g is 8e to the 4x. So we need to find g of x. So we are going to integrate 8e to the 4x dx. Well, this is another sort of chain rule, where the inside function is 4x right here. Now the derivative of the inside would have been 4, but there's not just a 4 hanging out outside, there's an 8. So I think the way to think of this is that you break that 8 up into a 2 and a 4 and say this is 2 4e to the 4x dx. So then when you integrate, like this 4 is the derivative of the inside, so you can do that backwards chain rule and say this is 2e to the 4x plus c. Now, the original function is f of x is equal to g of x is 2e to the 4x plus c. But now we're going to plug in this point right here, 2 comma 5e to the 8th. So that means you can get 5e to the 8th if you plug in a 2. Then this part just becomes e to the 8th, so you get 5e to the 8th equals 2e to the 8th plus c. So then you can subtract 2e to the 8th from both sides and get 3e to the 8th is equal to c. And that means our final function is g of x is equal to 2e to the 4x plus 3e to the 8th. Number 3, the rate of change of a fish population in a lake is given by dp dx. There's a couple of clues that they're talking about a derivative. A derivative gives you a rate of change. It gives you like the slope of a tangent, but it's also a rate, like slope is a rate. And this notation right here tells me that they took the derivative of p and got this. So you're looking at a derivative. It's only from 0 to 4, and the initial fish population was 140. That's going to come into play later. Find the number of fish after 4 years. Well, first, we're going to integrate 60t to the 1/2. Notice that I have changed the square root symbol into a power of 1/2 because now I can run my reverse power rule. This will be dt as well, derivative with respect to t. So this will be 60 times 1 over 1/2 plus 1 times t to the 1/2 plus 1 plus c. 1 plus a half is 3/2, and then when you turn it upside down, you get 60 times 2/3 t to the 3/2 plus c. 3 goes into 60 20 times. 20 times 2 is 40, so this is 40 t to the 3/2 plus c. So this is p of t, population of the fish after time t in years. Now the initial population was 140. That means if you feed in a t of 0, you should get out a 140, and thus we can solve for our t value. So 40 times 0 to the 3/2 plus c. This whole chunk right here is just 0. 0 to any power is 0. 0 times 40 is 0. So c is 140. So that means that our function p of t is 40 t to the 3/2 plus 140. They want to know what the fish population was after 4 years. So we're going to put a 4 into this function. Say p of 4 is equal to 40 times 4 to the 3/2 plus 140. When you crunch that out, you should get 460. Is the population just, it's not in thousands or anything like that? Okay, yeah, it's just 460 fish. So 460 fish when t is equal to 4 years. That's your final answer. Now, you guys, there's this process called U-Substitution. We've sort of been doing a baby version of it. Well, we haven't really been doing it, but we've been doing backwards chain rules. U-Substitution is for backwards chain rules. Well, I guess I don't need to put that arrow because I said it right here. Yeah, it's all about backwards chain rules. But I think up until now, the inside function has always been a linear function. Now, U-Substitution is really for use when the inside function is non-linear. Because when it is linear, you can just do like 1 over the coefficient to kind of balance it out, which we were doing in those problems up there. But now, when it gets more complicated, I'm going to show you U-substitution. Okay, here's how you know this problem is a candidate for U-substitution. When you look at it, there's an inside function. The inside function is 3x squared plus 7x, and it's being raised to the power of 5. So that means if you think about the original function, a U-substitution happened, and a chain rule happened to take the derivative. Remember, the chain rule is derivative of the outside with the inside untouched times the derivative of the inside. Now, you guys, do you see how this right here looks like the derivative of the inside? Like if this is our inside function, this is the derivative of that inside function. So it's like a chain rule happened. I'm going to show you guys this U-substitution method to be able to go backwards with this chain rule. The way you do it is you define the inside function as U. So you say, let U be equal to the inside function, 3x squared plus 7x. Now, I mean the inside function of like the something to the 5th power, not the inside function. Like this, the front part is the inside function. The back part is just the derivative of the inside. That means that this whole chunk right here is u to the 5th power. So 3x squared plus 7x to the 5th power is equal to u to the 5th. The next step of substitution is to find the derivative of u. So du dx is equal to 6x plus 7. Now, when you think about this du dx, so that's literally just the derivative of this right here. A derivative of u is, the power rule, bring the 2 out in front, and then the coefficient is just the 7. The way I want you guys to think of this is that, think of this like a fraction right here, and you could actually multiply both sides by dx to get du is equal to 6x plus 7 dx. Now, notice how this right here matches up with this. So this whole section right here, this is du. So what we're going to do is rewrite the entire function, but in terms of u. So it's still an integral, and then this will be u to the 5th du. Now, looking at just this function right here, this is very easy to integrate. We just use our backwards power rule. So this is 1 over 5 plus 1 times u to the 5 plus 1 plus c, which is equal to 1/6 u to the 6 plus c. Now, that is the integral in terms of u, but what we're going to do is replace u with what it was in the beginning. Like, we defined u as 3x squared plus 7x, but what we're going to do is take that and put it right here. So, what this means is that all of this is equal to, excuse me, 1/6 3x squared plus 7x to the power of 6 plus c. That was U-substitution. I'm going to do a couple more examples for you guys. Okay, this problem is a candidate for U-substitution once again because there's an inside function. X to the 5th plus 3 is inside cosine of x. So first step, define u. U is equal to x to the 5th plus 3, and then cosine of x to the 5th plus 3 is equal to cosine of u. The next step is to take the derivative of u. So you say du over dx is equal to 5x to the fourth. Now, what's tricky about this is that up in this original function, if there was a 5x to the fourth, everything would be hunky-dory and we could treat it like the last problem. The problem is there's no 5 in there. So the way you need to think of this is that you're kind of putting a 5 in here right here, but then you have to balance it with a 1/5 on the outside. The other way the book goes about that is being like taking this right here and saying, okay, we need just x to the fourth dx, because that's what's in here. We have an x to the fourth and a dx. So they rewrite that as, multiplying both sides by dx and dividing or multiplying both sides by a fifth. I mean, I guess I could do it in 2 steps. Say that that's a u. du equals 5x to the fourth dx. But we don't need 5x to the fourth. Once again, we need x to the fourth dx. I'm going to get rid of this 5 and this 1/5 just for now. So what you do is divide both sides by 5 and say 1/5 du is equal to x to the fourth dx. Then you can rewrite the entire problem using just u and saying this is integral 1/5 cosine u du. Notice that the x to the fourth and dx are right here, and they got replaced with 1/5 du. It's just I moved the 1/5 out to the front. Now you can run just your normal in backwards cosine rule. Remember that the derivative of sine is cosine, so the antiderivative of cosine is sine. So this whole thing equals 1/5 sine u plus c. Then the last step is to change things back out of the u notation. Remember back up here, use a different color. U was x to the fifth plus 3, so we need to replace this u with x to the fifth plus 3. So our final answer is 1/5 sine, and then inside function will be that u, which is x to the fifth plus 3 plus c. Next problem. The inside function is 3x squared, so that's going to be the u. We'll say that u is equal to 3x squared, and then e to the 3x squared is going to be e to the u. So this whole part right here will get replaced with a u. Now the derivative of that inside function, well, let's write it out. Du dx is 6x. So if I multiply dx by both sides, you get du is equal to 6x dx. Now, if you look up at the original function, we don't have a 6x, we have a 2x. So we need this 6 to change into a 2, but we're going to balance it by multiplying 1/3 on both sides. So we get 1/3 du is equal to 2x dx. Now, this part right here matches up with 2x and dx. So that orange part gets replaced with 1/3 du. So if we rewrite this whole function, we get, let's just bring the 1/3 to the outside, 1/3 integral e to the u du. Then we integrate that. Remember that the e to the x, derivative of e to the x is e to the x, and derivative of e to the u, or antiderivative of e to the u is e to the u. So it's the freebie. You can just say this is 1/3 e to the u plus c, but then we need to replace the u with whatever it was in the beginning, which is 3x squared. So this is 1/3 e to the 3x squared plus c. Last problem. It can be kind of tough looking at this to decide what the inside function is. So before we even define what u is, I'm going to rewrite this as 8x cubed minus 15x squared times 2x to the 4th minus 5x cubed to the negative 1. Now, if you look just at this function, this is the inside function because it's inside to the negative 1 power. If you were to take the derivative of the inside, you would get 8x to the 3rd minus 15x squared, which perfectly matches up with this guy. That means we're not going to have to reverse engineer too much because the derivative of the inside is already present. So we'll say u is equal to 2x to the 4th minus 5x cubed. And then that means 2x to the 4th minus 5x cubed to the negative 1 power is u to the negative 1. Take the derivative of u. That means du dx is equal to 8x cubed minus 15x squared. That's cool because that is right here, as we discussed earlier. And when I rearrange this, when I multiply both sides by dx, you get du is equal to 8x cubed minus 15x squared dx. So I can rewrite, I'm going to say this function, not the original, just the rewrite of the original. We can rearrange that into u to the negative 1 du. Because, oh, I forgot the dx on the end of that. Here we go. It was dx up here. So, this part and this part became the du, because that's what du is equal to, is this right here. Then this part right here, the something to the negative 1, became u to the negative 1, because we defined it that way here. Now we can run our power rule. Oh, wait. It doesn't work with the power rule because you get a 0 in the denominator. Oh, yeah, that's right. This is the same thing as 1 over u du, which means this is natural log absolute value of u plus c. And then we have to replace the u with whatever it was. It was 2x to the 4th minus 5x cubed plus c. All right, you guys, that was U-Substitution. Please ask me questions during class.